All right, let's go over this one. So I would rewrite everything to sine and cosine here. So that tangent is sine theta over cosine theta. Cosecant is 1 over sine. And secant is 1 over cosine. Straight multiplication, obviously these cancel. So you get 1 over cosine over 1 over cosine. Anything over itself is just 1.
I just split everything where
So when you're solving an equation, clearly you want to isolate your variable. So when it says we're solving by isolating the variable, technically that's what you're actually going to do anytime you solve an equation. You're isolating what you're trying to solve for. But the first one that we have here is rather simple. Keep in mind, when I am solving these, I am solving for theta, meaning I am solving for my angle. Typically on these, you want your angle in radian measure. So I'm looking for pi over 2, pi over 3, pi over 4, it's whatever. I'm looking for some angle in radian measure that gives me the sine or cosine or tangent that I have isolated, okay? So what I'm trying to solve for is technically the theta, but I want to isolate the trig function. So that means I want to get rid of everything on that side of the equation and leave the trig function by itself, okay? And so for this one, of course, I'm going to subtract a 1. I have 2 sine of theta equals -1. I'm going to divide by 2. So I have the sine of theta equals -1/2. What I'm looking for is theta, meaning I need the theta that gives me a sine of -1/2. All right, there are 2 quadrants that give me a negative sign. That is the third and the fourth quadrant, okay? There is one reference angle that gives me a sine of 1/2. That is pi over 6, okay? My 30-degree angle has a sine of 1/2. So pi over 6 is going to give me a sine of 1/2. Specifically, I need a -1/2, meaning I am going to look at the sine value in the third and fourth quadrant that give me a 1/2. So that's going to be my pi over 6's. So it's going to be 7 pi over 6, just past, you know, and then it's going to give me, 11 pi over 6. So I need the 30-degree or the pi over 6 angle in the third quadrant and in the fourth quadrant, which is going to be those two, right? So we have 7 pi over 6 and 11 pi over 6. 2 answers here. Now, we have what's called a primary and a general equation. Primary equation is what happens in one unit circle, okay? So if I ask for the primary answer to this equation, this would be it. My theta could equal either 7 pi over 6 or 11 pi over 6. That's primary. If it were to ask for general, it wants you to tell me every time it could happen in the entire function. Now your sine function is continuous, meaning it goes from -infinity to +infinity, and it looks like a wave. We have all graphed it, right? When will -1/2 happen? Well, it'll happen an infinite number of times. Specifically, it'll happen an infinite number of times every time you cycle through this guy or through this guy, right? And so if the primary is the what happens one time on a circle, the general is going to say, well, what happens in the cycle every single time? Well, basically you take this guy, 7 pi over 6, and you say every circle, every complete circle, I'm going to hit that guy again, right? And so, well, how do I say I'm adding a circle? Well, that's in these terms, a circle is 2 pi, right? Well, how many times? Well, every multiple of 2 pi, actually, that's going to happen. And so they put a little in here to represent every 2 pi, 2 pi, 2 times 2 pi, 3 times 2 pi, 4 times 2 pi. You are going to hit this answer every time you circle, right? The same thing will happen with 11 pi over 6. So you're going to say the same thing here. It's going to happen every circle from that guy as well. All right. And so if they say primary, they are saying, I just want what happens in one circle. Give me every single time this happens in one circle. If it says general, then it's going to say, take those guys and cycle through it. Now, I will warn you, sometimes it happens every pi, not every 2 pi. So, you know, it could happen every pi because you could have a first, third quadrant or a second, fourth quadrant, right? And it could happen every pi instead of every 2 pi. So you just have to be careful about how those cycles run, and we're going to do a couple of those as well so that you can see them pair up. But primary versus general, sometimes they'll say those words, and you need to pay attention to what it is. So in this case, they're actually wanting both. They want primary and general solutions here. When you see a tangent squared, you may be tempted to think about Pythagorean identity, and there will be times when we do replacements. The only time I would actually replace with a Pythagorean identity is if I had a tangent and a secant in the same problem. And then I'd be like, let's get this down to 1, potentially. But in this case, I actually would just isolate the tangent squareds is what I would do. So if you move your tangent squareds to one side, you're going to get 2 tangent squared of x. I'm just putting them in the order that I want. If I moved it over, it'd be negative and a negative 6, but I'm going to do a 2, a positive and a positive, by the way. So you'll get something like that, right? And so isolating it would be to divide it. You'll get tangent squared of x equals 3. How do I solve when I have a square? Well, I take the square root, which is exactly what we're going to do here, the square root of this and the square root of this. But remember, when I take the square root with a variable involved, I have to consider the positive and negative root. Okay? Tangent, square root of 3. So tangent is sine over cosine. So we're going to obviously be either a pi over 3 or a pi over 6. And so you have to think about the pi over the radian that gives you a square root of 3 on top, because that's what happens for tangent. Your numerator will keep change flip is what will happen. So square root of 3 over 2 over 1/2 would actually give me, when you reduce it, a tangent of square root of 3. And that happens actually 4 times if we're talking positive and negative, because I'm looking at where it's positive and where it's negative. Well, tangent is positive in the first and in the third quadrant. So whatever angle gives it to me is going to be both the first and third. And then it is also negative in the second and fourth. And so whatever gives me a square root of 3. These are my pi over 3s, or my 60-degree angles that give me these. So my positives are going to happen at pi over 3 and at 4 pi over 3, right? That's going to be the positive, positive, negative, negative. And then the negatives are going to happen at 2 pi over 3 and at 5 pi over 3. And so you get a picture of this when you do that right there. So you see that I have a positive square root of 3 tangent here, sine over cosine. They reduce to pi over 3, just square root of 3. And I'm also going to get the same thing when I do negative over negative. That's going to give me a square root of 3. A negative happens here. Positive over negative, negative over positive. That's going to give me my negative square root of 3. So it's going to happen in all 4 quadrants when I look at positives and negatives. It's going to flip-flop. Now, here's what I mean by cycle. This is going to be my primary solution. All right, this will be my primary solution. Those 4 answers would be my primary solution. But what if I wanted to do a general? Well, your brain would probably say, take each one of those and cycle by 2 pi. But they pair up. Right? So technically, this is only 1 pi away from that, right? And so it's going to happen at 1 pi and at 2 pi and at 3 pi, 4 pi, 5 pi, 6 pi, right? I'm going to hit those 2 every pi. So I can actually just take this first guy for my general solution. I could say, well, we could just take pi over 3 and add a half a circle to it. And that would get me to 4 pi over 3, right? And so then I can just do multiples of pi, because those are just 1 pi apart. And I can do the same thing with 2 pi over 3 and 5 pi over 3. If I take 2 pi over 3 and add half a circle, I get my 5 pi over 3. So for general, I don't need to list all 4 of them. I just need to list the first one and multiples of pi, right? A half circle. And so again, I can just say, well, plus multiples of a half circle there, right? I don't have to list all 4 for my general, because the first 2 encompass it if I just multiply by pi, or add pi rather. So when we do solving by factoring, there's a couple things to keep in mind. There are times when you really need to rewrite it. And then there are times when you could factor and isolate your two different trig functions. So they actually give us each type of example. When you're solving by factoring, think about just your basic quadratics that we've done before, where I might have to do my binomials. So, x squared plus 5x plus 6 is x plus 2, x plus 3, right? I have to do two binomials. And then you set each one equal to 0. So anytime you're solving by factoring, your goal is not to get the variable on one side and the number on the other. Your goal is actually to get everything to one side and set it equal to 0, right? And so the other ones that we've been doing, we could actually get our trig function by itself and then figure it out. In this case, you have too many trig functions to try to get by itself. So you're really going to want to get all of them on everything on one side, set it equal to 0, and then factor and set each factor equal to 0. And then you'll have a smaller equation that you can deal with like we've been doing for the first two examples. Now this first one is different because I have a sine and a cosine, and I really can't isolate either one of them. And so this one, I am going to use Pythagorean identity to get only one type of trig function. So I have sine squared. I can rewrite him as a cosine, and then I'll have a cosine and a 1. And so everything on that left side will be cosines, and then maybe I can deal with it then. And so my first step here is going to rewrite this sine squared in terms of Pythagorean identity. Now, just a reminder, it's sine squared plus cosine squared equals 1. So if I want to replace the sine squared, I'm going to replace it with 1 minus cosine squared, right? And so I'm going to replace this whole thing here with 1 minus cosine squared of x. And then I have the cosine x plus 1 equals 0. I will say here, so I'm going to, I'll show it out. So I have negative cosine squared of x plus cosine of x plus 2 equals 0. I never factor with a negative in front. I just don't. So I actually would take that negative out of everything, divide everything by that negative, so that I have a positive cosine squared of x, a negative cosine of x, and a negative 2. All right. Basically, you want factors of 2 that subtract to give you 1. Right? That's going to be a negative 2 and a positive 1, right? So just think of it as x squared minus x minus 2. That's what you're thinking of, okay? So you know that you're going to have your cosine of x, right? And then you really just want factors of 2 that multiply to give you negative 2 and add to give you negative 1, right? And so that's easy. Right? So when you see the trig function in there, just think of it as a variable squared plus a variable plus a number, something like that. And now we have something rather simple to solve. When you're solving by factoring, you set each one equal to 0. So I'm going to say, well, cosine of x minus 2 equals 0, and cosine of x plus 1 equals 0. Cosine of x equals 2. We have a problem. What's my domain for cosine? There is no cosine, there is nothing that gives you a cosine of 2, okay? The largest your cosine can be is 1. And that makes sense because remember, it's based on right angle trigonometry. Your hypotenuse is your largest, and it's a number over your hypotenuse. All right, so there's no way that number can be larger than the hypotenuse. It's impossible, all right, which is why your 90 degrees give you your 1s. All right, so this one's not possible. So this one will not provide a solution. I can just cross that guy out. He's not going to give me a solution. No solution for that. There is no angle that gives me a cosine of 2. The other side is going to give me cosine of x equals negative 1, all right? That happens one time on your unit circle. Where do you have an x value of negative 1 on your unit circle? When that equals what? Pi. And that is my answer there, all right? When x equals pi. If I wanted my general solution, it would be every circle. So pi plus into 2 pi, all right? So every circle of that would give it to me. So that's one way where you're possibly going to need to rewrite it using Pythagorean and factor it out. Look at the next one. So the next one seems to be completely disjointed. We have tangents and sines. That doesn't help me with Pythagorean identities for sure. I am still going to get everything to one side because I am still solving by factoring. So I'm going to move this guy over and I'm going to have 2 tangent x sine x minus the square root of 2 tangent x equals 0. I can solve by factoring here. This is basic factoring. What can I take out of each one of those groups? What do they have in common? They have a tangent of x. So I'm just going to factor out my common factor, which is tangent of x. Tangent of x comes out here. I am left with 2 sine x on that left, and I'm left with just a square root of 2 on the right, okay? And now I can set each factor equal to 0, plain and simple. So tangent of x equals 0, and 2 sine x minus the square root of 2 equals 0. Where does my tangent of x equal 0? Well, everywhere that my y value is 0, right? There's 2 places on the unit circle where this happens. It happens at 0 and pi, actually. So it's going to happen, right? So yeah, it's start with 0 and then all the way to pi. But 2 pi is the same as 0. But it does happen at 0 and at pi. That's where those happen, right? And then this one I'm just going to solve. So add the square root of 2, divide by 2. The sine of x equals the square root of 2 over 2. All right. So there's 2 places where my sine on the entire circle is positive square root of 2 over 2. Those are the easy ones. Those are pi over 4s, right? First quadrant is going to give me pi over 4, right? And then it happens again in the second quadrant. My sine is still positive there. That's at 3 pi over 4. So those are my 4 possible answers for this one. 0 and pi from the tangent piece of it, pi over 4 and 3 pi over 4 from the sine piece of it. So in this case, once again, we are trying to isolate my trig function. This one's rather simple to isolate. I just have a 2 being multiplied in front of it. So the cosine of 3x equals the square root of 3 over 2. Here's the thing. I have this variable within my trig function. So when you first do this piece of it, you are going to ignore that 3 in front of the x. You basically just want to say, okay, what angle, though, will give me a cosine of square root of 3 over 2? All right, well, that's going to be your pi over 6s, all right? Right? Your pi over 6s give you a cosine of square root of 3 over 2. Your 30-degree angles give you a cosine of square root of 3 over 2. It's positive. So specifically, I need first quadrant cosine and fourth quadrant cosine. Those are my positive cosines, right? And so my angle that I'm looking for that will give me this is going to be my pi over 6 and my 11 pi over 6, right? So those two will give me a square root of 3 over 2 as a cosine. But that doesn't equal x. That actually equals 3x. So I have, well, 3x equals pi over 6, or 3x can equal 11 pi over 6. Because that's what the angle is right now. My angle inside my cosine is 3x, not x. And so I'm not quite done yet. I still need to isolate the x, right? And so to do that, I'm just going to divide both sides by 3 or multiply by 1/3. So if I multiply this guy by 1/3 and multiply that guy by 1/3, do the same thing over here, then you'll see that your x is actually going to be pi over 18 or 11 pi over 18, because I'm not quite done yet, right? if I were doing a general solution here, I would actually write my general solution first. So just want to show you that. So if this were where I was the point at which I got 3x equals pi over 6, and I want the general, right? So that's going to happen every pi. I'm not going first and fourth quadrant, or first and third quadrant, right? That would be happening every pi. I'm going first and fourth. So I actually have to add a 2 pi to this guy. And I would have to add a 2 pi to this guy. And you would actually then divide everything by 3. So you have to consider you're not doing it at the end. So you don't want to add the 2 pi at the end. You actually want to add it before you divide by the 3, because that cycle happens before you do that. And so you would actually have to divide everything or multiply everything by 1/3, not just your piece there. So you would have like pi over 18 equals n 2 pi over, or plus 2 pi over 3, something like that. 11 pi over 18 plus n 2 pi over 3. So you would wait till you actually set it up to divide by 3. So primary would just be these guys, the 2 times that it happens, but at the end, divide by that 3. General would be set up the general first and divide every piece of the general solution by 3. All right.